Welcome to the deep dive. Today, we're getting into a really interesting technical report. It's the one on Qwen 3 Omni. This paper lays out how they built a unified multimodal model, aims to change things up a bit. So our mission, for you listening, is to pull out the key mechanical insights. How does Qwen 3 Omni supposedly hit state-of-the-art across text, image, audio, and video without that usual performance hit? The degradation you normally see when you try to cram everything into one system.
Right, that's the core claim, isn't it? Non-degradation. And it's a big deal because, well, historically, these big multimodal models, the ones built on LLMs, they always seem to have these modality trade-offs. You improve one thing, like vision, and maybe the language side suffers a bit, or vice versa. Win3 Omni was apparently designed from the ground up to sidestep that whole problem through its architecture.
And the architecture sounds pretty novel. They call it a thinker-talker mixture of experts. MOE, can you bring that down? The thinker and the talker roles.
Sure. So think of the thinker as the brain, basically. It handles perception, understanding, reasoning across all four modalities. Text, image, audio, video, it takes it all in. Then you have the talker. That's the output module. It's specialized in generating high-quality speech and audio. So this structure, it unifies the perception and the generation across the board.
Okay, so it's not just slapping modalities onto an LLM. It's a more integrated design with these two MOE components.
That's the idea. Distinct roles, but tightly integrated.
So what's the payoff then? The report talks a lot about speed and capacity, long context capabilities, like processing audio recordings up to 40 minutes long. For things like ASR and understanding spoken language and videos, that sounds computationally heavy.
Oh, it absolutely is. 40 minutes of audio is a huge sequence. But the speed they're reporting is maybe the most surprising part. They claim a theoretical end-to-end first packet latency. So how quickly you get the first bit of response of just 234 milliseconds. That's in a cold start scenario, single user. For a model this complex, that kind of responsiveness is, well, aiming for real-time interaction, less of that typical chatbot lag.
How do they achieve that? What are the architectural tricks enabling that speed and efficiency? It can't just be the MOE structure itself, can it?
Well, it's how they've upgraded the MOE structure. Both the thinker and the talker use these enhanced MOE designs. These are specifically built to handle high concurrency, lots of users at once, and faster inference.
Okay, faster inference. How does that tie into handling, say, that 40-minute audio file?
It's really about memory. The key value cache, or KV cache. When you process long sequences, this cache stores intermediate results, and it gets enormous. The upgraded MOE design apparently slashes the input-output needed to access this KV cache. Less data shuffling back and forth. That's a huge bottleneck, especially for long inputs. So reducing that I/O is key to keeping things fast, even with massive sequences. It's a core efficiency gain.
Makes sense. And what about the output side, the talker? You mentioned it handles speech generation. Any innovations there?
Yeah, quite a bit, actually. They're still using a multi-codebook autoregressive approach, which is fairly standard, but they ditched the older, very compute-heavy blockwise diffusion method for generating the audio waveform. Instead, they use a much lighter causal concept. They call it code-to-wave.
Code-to-wave, so lighter means faster.
Right. Blockwise diffusion has to process audio in big chunks. You wait for the whole chunk before you hear anything. This code-to-wave, being a causal content, can start generating the audio stream right from the very first little piece of code, the first codec frame. That directly contributes to hitting that low first packet latency. You're not waiting around for a big chunk to finish processing.
Okay, that's clever. And they also mentioned something about decoupling the thinker and talker using system prompts. How does that work?
Yeah, so the thinker figures out what to say, the content, the meaning. It sends that high-level information to the talker. But the talker can use its own separate system prompt.
And the advantage there is?
Control. Granular control. You can tell the thinker respond formally or be conversational. That controls the content style. Then independently, you can tell the talker use this voice or sound enthusiastic or speak with this accent. That controls the audio style. So you separate the what for the how it sounds without making the giant thinker model also learn all the nuances of voice styles. It keeps things manageable.
I see. So moving from the how to the what results. Where does this model really shine, according to the report? The audio domain seems to be where they're making the biggest claims.
It really is. The numbers are pretty eye-opening. They're reporting open source state-of-the-art on 32 out of 36 audio and audio-visual benchmarks, and overall SOTA beating even closed-source models on 22 of those.
Which closed source models are we talking about?
Well, they name names. Gemini 2.5 Pro, Seed ASR, even GPT-4o Transcribe. outperforming them on tasks like transcription, voice chat, music understanding. It suggests a really significant step forward in just handling audio signals effectively.
What's behind that audio leap? Did they just tune something existing?
No, they actually swapped out a core component. They replaced the standard Whisper audio encoder with their own proprietary one. It's called Audio T for Audio Transformer.
Trained from scratch.
Yep. On a massive data set, 20 million hours of supervised audio. The claim is that this AUT encoder builds much stronger, more general audio representations, better foundations. And when the encoder is that good, all the downstream tasks, transcription, understanding, etc., they just perform better.
And does this audio strength cover multiple languages?
It seems so. The language support overall is pretty broad. Text interaction in 119 languages. For speech specifically, understanding in 19 languages, Chinese, English, Arabic, Japanese, Korean are mentioned, and speech generation in 10 languages.
Okay, so strong audio, broad language support. Let's circle back to that central idea, non-degradation. The report insists that Qwen 3 Omni hits SOTA on text in Vision 2 without losing ground compared to their specialized models of the same size, like Qwen 330B A3B base. So the multimodal training didn't hurt the individual modalities. How did they pull that off when others struggle? What's the mechanism?
They point to one key strategy during training. It wasn't just about fine-tuning at the end. It was about mixing unimodal data, just text, just images, just audio, with cross-modal data, right from the early stages of text pre-training.
Early stages, so not an afterthought.
Right. By doing this co-training early, the model supposedly learns shared fundamental representations that work across different types of input. This joint training apparently allowed them to reach parity across modalities, and sometimes even improve things.
So rather than teaching a language model about pictures later, it learns cat from text about cats, pictures of cats, and maybe cat sounds, all kind of woven together from the start.
That's a good way to put it. And they found something else interesting. Adding the text modality seemed to actively boost performance in vision and audio. Text acts like a sort of structural anchor, making the model better at the other modalities too. It's strong evidence against needing strict specialization.
Fascinating. Okay, lastly, the report mentions some specialized variants. Built on top of this Omni base, there's a thinking model, Qwen 3 Omni 30B A3B thinking.
Yeah, this one is specifically tuned for more complex reasoning across modalities, thinking deeper about the combined inputs. Interestingly, while it's better at reasoning, they note the standard instruct version is actually better at raw perception tasks, like ASR, different jobs.
And there's also a captioner model.
Qwen 3 Omni 30B A3B Captioner.
Yeah.
This one is fine-tuned specifically to generate detailed captions for audio inputs with low hallucination. They specifically say this is to fill a gap because most captioning research focuses on images, not describing complex sounds accurately.
Okay, so wrapping this up, what's the main takeaway from this technical report?
I think the big message is that Qwen 3 Omni offers pretty strong evidence that you can build these deeply integrated end-to-end multimodal models. Without paying that performance penalty we've almost come to expect, you don't necessarily have to sacrifice language skill to get good vision or audio skill or vice versa if you integrate them early and correctly. It's a potential milestone.
Right. It definitely challenges that idea of unavoidable trade-offs. So a final thought for you to consider. If this report holds up, if early multimodal integration really allows co-training without degradation, how does that change what we should expect from all foundation models moving forward? Does this push us away from specialization towards truly integrated intelligence as the new baseline?